So this presentation is going to focus on the concept that spin drift and round tumble play significant roles in drift compared to crosswind drift. So we'll focus on the 30-06 round with the typical 150 grains bullet mass fired out of a 24-inch barrel 30-06 bolt-action rifle. So using engineering physics analysis methods, starting with kinematics, we need to calculate the gravity drop of the round if fired from a 0 degree angle approximately 4.5 feet above the ground, which is the average shooter height distance fired from the shoulder. The gravity drop can be described by the change in distance on the y-axis is equal to 1/2 gt squared, so that is the vertical axis. So if this bullet was not moving and we just dropped it on the ground, how long would it take for it to fall 4.5 feet? So we can use delta D on the y-axis is equal to half of gravity multiplied times time squared. So we input consistent units. 4.5 feet is equal to 1/2 32.2 feet per second squared gravitational acceleration on Earth vertically downward, then times t squared. So by substitution, this equals 4.5 is equal to half of gravity, 16.1, times t squared. So we can then divide 4.5 into 16.1, moving 16.1 on the left side, made equal to t squared. And then t squared will equal 0.2795. So that means the square root of 0.2795 is equal to t. So it takes 0.53 seconds for this bullet to drop and hit the ground. But now, when we're dealing with projectile motion, the initial velocity is more or less equal to the final velocity. The only limitation is that the slight rise on the parabolic motion, this is half of a parabola, by the way, will limit the vertical component, the vertical velocity. So we're focused on only the horizontal velocity. So gravity combined with the horizontal projection then keeps a constant horizontal velocity. That being said, the complete flight time of the round is equal to the drop time, 0.53 seconds. So at 3,000 feet per second multiplied times 0.53 seconds, the round will have a range of 90 feet if fired at 0 degrees angle from the horizontal. So of course we could use the range equation if we were to angle this higher than 10 degrees, but we're doing this as a theoretical 0 degree range model where gravity is the limitation. So the established range is 90 feet. And so the point of interest is to compute how much round or bullet drift the given application will have if applied to a 30 mile per hour crosswind. So we notice the vector is perpendicular crosswind to the vector of the bullet's motion forward. So we would assume there would be a drift if the crosswind is coming in from the east, pushing the bullet drift to the west. So the next thing we need to do is focus on the bullet geometry. So the average 30-06 round will have a 1.1 inch bullet length independent of the shell casing. And then we know 30-06 is 0.308 inch diameter or caliber. So we have to figure out the drag coefficient of airflow over the side of a cylinder. So if we were to look at the bullet from the rear view, the crosswind is flowing perpendicular, let's say from the east, and then going over the circular projected frontal area to the west. So we go to the Aerospace Shapes Handbook and we look up the aerodynamic drag coefficient of a cylinder sidewall, and that is approximately 0.3. Then we also need to know how to compute the projected frontal area of the side. What is that curved surface area approximate value? So that is calculated by 2 times radius times height. So in this case, the height would be the length, and then the radius is half the caliber, half the diameter. So we can take 0.308 inches, divide it by 2, multiply it times 2, multiply it times 1.1. So we calculate a projected frontal area on the side of the round of 0.3388 square inches. We can take its square root here to get the linear inches, divide it by 12, and then square that value, and so we get the square feet. Then we can go to the aerodynamic drag force equation, which is the pounds drag airflow incurs upon a structure. And this is the derivation of the kinetic energy equation, 1/2 mv squared, but it's set up for aerodynamic applications. So we take the drag coefficient times the projected frontal area in square feet, then times the air density, but it has to be in slugs mass per cubic foot. So we can take that from pounds mass per cubic foot average air density, and then multiply it times the crosswind speed in feet per second quantity squared. This entire product numerator sum is then divided by 2. So we have 0.3 for drag coefficient. We have 0.00235 square feet for projected side area, but that will be the frontal area since it's crosswind. And then we take the average air density across the atmosphere of 0.07406 pounds mass per cubic foot. Then we divide that value into 32.2. There are 32.2 pounds per 1 slug absolute mass value in the US system of measure. So this is a very typical average value for air density and slugs per cubic foot, 0.0023 slugs per cubic foot. So we enter that in for rho air density here, and then we convert the 30 miles per hour to feet per second. So there are 22 feet per second for every 50 miles per hour. So that's 44 feet per second quantity squared divided by 2. So we calculate a crosswind drag force of 0.0016 pounds force. So now we're done with the aerodynamics portion of the engineering physics analysis. Next thing we need to know is to calculate the force accelerating the round that will be designated as the bullet forward force. We know the crosswind drag force. So we use Newton's second law of motion. Force is equal to mass times acceleration. So we take the 150 grain round from the 30.6 bullet mass, multiply it times 64.8 milligrams per grain. We calculate 9720 milligrams. We convert this into grams, and then we convert this into kilograms. Next, we need to know the firing time. This is the barrel length D divided into the muzzle velocity V. So the barrel length is converted from 24 inches to 2 feet. Muzzle velocity is kept as 3,000 feet per second, but we'll just side convert it to its meters per second value by dividing it into 3.28, so 914.6 meters per second muzzle velocity. Then we solve for the acceleration, which is velocity, final velocity divided by time. So it starts at rest and reaches the final velocity of 3,000 feet per second, or 914.6 meters per second. We divide this value into the firing time, So again, the firing time is the length of the barrel D divided into the muzzle velocity V. So 2 feet into 3,000 feet per second is a firing time of 0.00067 seconds. Feet divided into feet per second cancels out into seconds. So then we have the acceleration value of 1,365,075 meters per second squared acceleration. We then multiply this value times the kilograms mass of the round. We calculate 13,269 newtons of force, for which we divide into 4.45 to get the pounds force, accelerating the round, so it's 2982 pounds force. So next we move on and draw a two-dimensional vector sum. So in this case, we have the first projection, which is the force accelerating the round. We always add vectors head to tail, so theoretically the crosswind's coming out from, let's say, the west, but we could also flip it around to the east. So we add the vector head to tail. Now we have a diagonal hypotenuse. So from that point on, we can only use this information to solve for the angle. If we were to use the Pythagorean theorem to solve for the resultant, it would be very close to the force and thus negligible. So if we look at the relevant sides, the projection of the bullet is the adjacent side because we're making an angle, and then the perpendicular side is opposite to the angle, so this is the opposite. And then the diagonal is always the hypotenuse. So now we have the angle sides identified correctly. So the relevant side is adjacent and opposite. So when we're dealing with opposite and adjacent, O over A, that is tangent. Cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse. So we'll use tangent. So in this case, we can divide the opposite side crosswind drag force into the force accelerating the bullet. And then we have the tangent theta, some angle unknown, equal to this ratio value here, 0.0016 divided into 2982 equals this value here. Then we use the inverse tangent of the value we calculated. We get a very, 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 very tiny angle drift caused by the 30 mile per hour crosswind because the surface area of the side of the bullet is so negligible. So then we reapply this such that we have the crosswind identified on the west to east vector as we intended. We just limit 100 feet of range for the adjacent. The opposite is the crosswind drift with respect to the angle we calculated, and then we have the hypotenuse on the top. So now we just apply tangent once again, opposite over adjacent. So in this case, it's x opposite over adjacent 100 feet. X over 100 is equal to the tangent of the angle we calculated up here. So we solve for x by multiplying the tangent of the small angle times 100, tangent of this angle times 100, and so we calculate a very tiny amount, a feet drift per 100 feet range at 30 mile per hour crosswind. Then we take this value and we multiply it times the multiples of 100 over the range of 1590. So 1590 over 100 times this value here. So we have it here. We calculate a total drift of this small value here over the 1590 feet range. And then we then multiply this times 12. So we calculate a very tiny inch drift. And then we can go farther into the millimeters drift. So we know that the crosswind drift is more than likely negligible, even though it's commonly perceived as the crosswind having effect on a high energy or high powered rifle's performance, which on the computational level is relatively not proven or disproven. So we identify a 0.26 millimeter drift at 30 mile per hour crosswind over 50-90 feet range for the 30-06 rifle. So the conclusion is a typical 30-06 round has a gravity drop of 0.28 inches per 100 feet of range and crosswind drift of 0.26 millimeters at 30 mile per hour crosswind. So the spin drift, tumble, and shooter handling play greater roles affecting drift compared to crosswind. So the spin drift is just the rotating round as it passes through the lands and grooves, and then it sets up its own equalized centrifugal forces, and there is some aerostatic properties that project thrust outward evenly across 360 degrees, but it's not perfect. And so then you also have the principle of precession and not so much torque unless there's friction with the air. So depending on what direction the spin is, you're also going to get more significant drift from the spin itself, so spin drift. And tumble is just the irregularities through the barrel. And if it's a high tolerance, high performance, superior material system, then the tumble will be minimal. But then again, that goes into many tolerances that repeat themselves into error and correction. So then the precision versus the accuracy creates some sort of an error, and then there's a slight amount of tumble. So more than likely, the excessive drift of all projectiles, especially firearms projectiles, are actually affected more from the spin drift and the tumble, including the shooter handling compared to the crosswind. Thank you for watching this presentation and have a great day.